At some point, you were probably told that a tertiary carbocation is more stable than a secondary carbocation, which is more stable than a primary carbocation. But have you ever wondered why that is? And I've asked many people this question, and they give me these answers such as hyperconjugation or it's more bonded to more substituents. But what does that really mean? Well, if you think about it, you could think of these side groups as electron clouds. So if you picture this methyl group as a giant electron cloud, this one is also one, and also this one. You can also do the same thing with this secondary one and this primary one. Now, if you look at this, since there is electron density around the carbocation, it can essentially donate its electron density to the carbocation. So if we draw these arrows here, it's kind of donating towards it. And this is how I think about it in my head, and it helps me remember if it is being stabilized or not. Now, this concept might seem rather easy, but if we apply it to certain scenarios, we can kind of get a sense of what the most stable carbocation is. So let's say you're given this example over here, and your main goal right now is to figure out what the major product of this reaction is. So first we have to draw these electrons going from here to the hydrogen, and this bromine comes off. And then now you're stuck with two different carbocations, and you have to figure out which one is the more stable carbocation, which will make the more stable or the major product. So let me draw. You have the choice between this carbocation or this carbocation. Now, which one is more stable? Well, we can think in terms of electron density clouds here. You have electron density on one side, and then you have the electron density on this side. And then for this one, you have some over here, and then you have some over here. But if you think about it, remember that resonance is going on around this carbonyl group here, or this ketone to be exact. So the electrons are going up, and then this, you have a structure that looks like this. You have this here, and then you have this positive charge over here. Now, if you think about it in terms of electron density, what's happening is, let me get the right color here. What's happening is there's electron density still here, but because of this resonance, the electron density moved up more towards here. So there's less electron density over here, and thus it's not being donated over here. It's being withdrawn up to this oxygen. So because only one side is being donated, it's only being stabilized on one side. So you can kind of think of it in terms of these arrows over here. This is donating. Well, let me draw it on the bottom. This is being donated over here, but here the electrons are moving up. So only these electrons are being donated towards the carbocation, making it or attempting to stabilize it. And these electrons over here are being withdrawn because of the oxygen. Now, if we look at the bottom structure over here, you get this when it is being resonated. You get this structure. Let me draw the oxygens over here, and this positive charge over here, and you have the positive charge over here. Now, if you think about the electron densities, you have some over here. I keep forgetting to switch the colors. You have electrons over here, and you have electrons over here. Now, this carbon is far enough away from this carbonyl that it does not experience the electron withdrawingness of the oxygen. So here, the electrons are they're still partly over here, and this one is not affected by this at all because it's far enough away. So here, you have electron density. You have electron density going towards here and towards here. So what does this mean? Well, this means that obviously this carbocation structure is more stable than this one. That means that the most stable product has to come from this structure. So what is the product then? Well, since we got this hard part away, all we have to do now, remember we made bromide. So all that happens is this comes over here, and you get the product, which is something like this. Oh, let me draw that better. Something like this. Now let's say we have another example over here. We have this other example. And now let's say you want to react, well, let's just take HBr again because HBr is so fun to play with. So we have HBr over here, and then we drew the reaction again. These arrows go to the hydrogen over here, and then this happens. Now we have to find out which carbocation is more stable. So I'll go ahead, maybe on your paper you could do this ahead of time. You could pause the video and try to draw the two carbocations, but you don't have to pause it if you don't want to. I'll just draw it for you because I'm a nice person. Anyway, you have this carbocation over here, or this carbocation over here. Let me draw the electrons here. Let me draw it more visible so you can see what's going on. Okay, so which carbocation is more stable? Well, we can think of it in terms of electron density again, because why not? You get the better visual, and you get to kind of see what's going on throughout the structure. So we have electron density here, and we have some here, and we have some here, and we have some, well, we have some here. This oxygen. I know I kind of blocked it here. I'll just draw it later. Okay, that's an oxygen. Okay, so what's happening here? What is exactly happening here? Well, we got electron density. We got electron density on this side, and we got electron density on this side. We also got electron density here and electron density here. But because these electrons here can resonate to the carbocation, because this oxygen has lone pairs that it can donate. So what we can do is we can draw this over here, and then the structure we will get is this structure. Let me draw it in the right color. This structure over here, and it has electrons here, and remember there's a positive here, and here you can't really do anything with this carbocation here, because even if you resonate it, well, first of all, you can't resonate it, so this carbocation is just stuck on this carbon, whereas this carbocation can be resonated up to the oxygen. Now, if you remember, you would rather have an oxygen have a positive charge than a carbon. So therefore, this product, or this carbocation, is more stable than this one. And it kind of makes sense because in this case, this oxygen is an electron donating group, whereas our previous example, this oxygen over here was being an electron withdrawing group. So what's happening over here is that because this oxygen is an electron donating group, it is stabilizing the carbocation more so than if it was just a simple carbon. So what is our final product, you say? Then our final product, judging from this structure, has to be this final product, if I can draw it, this product over here, Br. Oh, I forgot. Remember, you have to draw the mechanism, right? Br minus, and then what happens is Br goes here. And then there you have it. So this is the more stable product because you're using this. I just made that more complicated. Well, you know what's going on. This plus, and then it goes down, and this is your final product.